Okay, everybody, moving on to Unit 10. And we take a break from the normal chemistry flow of moles and solutions and gas laws and looking at the atom. And we look at the atom a little closer now. We look at the nucleus of the atom and the changes that take place in the nucleus. And this subject is commonly called nuclear chemistry. It's not really chemistry, but it's more nuclear science where we look at the changes in the nucleus of an atom. And again, this could be a good thing to be used for or a bad thing, and it has a lot of debate to it. But it's a simple look at what happens, in the nucleus. So let's just take a look at some general ideas about atoms in general. Okay, and we look at something called natural radioactivity, and again, you may have done some work on this in another class maybe, but when we look at elements and where they were created, we look at them really being created in the cores of stars. Okay, so when you get these big explosions within the universe, you get atoms created from particles, protons and neutrons, that are mashed together into nuclei, and that's how they form. So, when the universe first exploded into what it is today, we had this big influx of elements being created. All right, so the very high pressures and the high temperatures typically drive these protons and neutrons together, and they come together and they create these new nuclei. But sometimes these nuclei are actually unstable. There's an instability with the numbers of protons and neutrons, or actually the size of the nucleus, and that nucleus cannot continue to exist in its current state. So what happens is that this nucleus begins to break down and emit energy, or pieces of itself, or particles, to, in effect, reach some type of stability, some type of resting point. Okay? So we didn't know about this until roughly 1899, when Henri Becquerel, you don't really have to know his name, we'll call it Henri B. Becquerel. What he did is he was working with a rock that contained uranium in it, atomic number 92, and he discovered by accident that there was energy just radiating out of this rock without actually putting energy into the rock. So this strange energy was strange to him, and realized that eventually there was particles, okay, and energy coming out of this rock just by sitting there. Okay, Marie Curie eventually, took this idea of this radiation or this radioactivity or this energy, and ended up discovering, other elements. So she ended up discovering the element radium, number 88. So again, we had this idea around 1899 that this radiation existed, but before that, we didn't know. Okay, so really what do we talk about? Well, what we find out is that all of the isotopes, and again, isotopes, remember, have different number of neutrons, all isotopes of atomic number 84 and higher are going to be unstable. So this includes all of the isotopes. That's not to mean that other elements can't be radioactive or be unstable, but not all their isotopes are. But when you get to 84, all of them are unstable. Okay, now what happens when you're unstable? What we do is you want to get stable, and the only way you can do that with a nucleus is break down or decay. They use the word for decay. Spontaneously means on its own. Okay, and what you do is this nucleus will emit particles and or energy to become stable. We talked about that a little up here. Okay, so the name radioactivity really, I believe, came from Marie Curie when she used this activity idea, is really the decay of a nucleus into a different nucleus. Now let's think about that for a minute. When you go into a different nucleus, when you lose particles from the nucleus, if you lose protons or you emit protons, you change the atomic number. So in this particular subject of nuclear chemistry, you can change one element to another. The element actually changes into another element by the emission of the particles. Now, this change, or this change from one element to another, has a special name. What we call it a transmutation. A mutation is a change. Trans means across. So you actually change from one element into another by changing the atomic number. Now, this doesn't always have to happen, but commonly that's what happens when you do this. Okay, so and just to keep in mind that at this point in time, so far. And again, this is huge areas of research in this subject. At this point, no human involvement can really affect the radioactivity, which means we cannot stop this. So if polonium is radioactive and it's going to change and give off particles or energy, we can't go and stop it from doing this. It's going to do this anyway until it becomes stable. So this is a naturally occurring thing. Okay, so a way you can write a short little reaction from this, a nuclear reaction simply, or a natural reaction, is we could take our unstable nucleus, okay, and then we draw an arrow, and that changes into a new nucleus and some type of emittal particle and or energy. Okay, again, usually energy is emitted by the process also. Now, this new nucleus may not be stable. It just is more stable. Okay, I would say more stable than it was before, or it could be stable. So this can be done in steps. This doesn't have to be done all at once. This could take stepwise. So you can do this once, and then this new nucleus can again, repeat the process and so on until you get to a stability point. So this can be a series of steps, or this can happen all in one step. Okay. All right. So just a couple of things when we look at types of radiation, what this radiation can do is when this radiation is emitted, okay, we can use the term ionizing power for this ability of this radiation to impact other things. So as this radiation comes out of this element, okay, it can hit other neutral atoms and simply knock the electrons off from the impact. All right. Again, imagine something flying across the room and slamming into something and just knocking it over. When this radiation hits and knocks electrons off of something, then that molecule, that atom, becomes an ion. All right. So, a positive ion actually, because you're knocking electrons off something. So remember, when elements lose electrons, become positive ions. Well, sometimes this radiation could be the reason why it does this. Now, the larger the particle of incoming radiation, the higher the ionizing power. So the bigger the nuclear particle, the bigger the radiation as far as the size of it, the bigger the impact. Like again, if you get hit with a larger object versus a smaller object, the likelihood of getting impacted from this is going to be greater. All right, so radiation hits an atom. Again, an atom would be a neutral atom. Okay, you can think of this as becoming neutral because it has an electron attached to it, equal numbers of protons and electrons. Okay, and what that's going to become is that's going to become an ion. Okay, and then that electron is lost. So the separated electron goes this way, and now this ion now becomes a positive charge. That is a good thing or a bad thing. Okay, that is a good thing if you want to use some type of electrical conductive material here, because this will conduct an electrical current. However, if this is a useful molecule that's in your body, in your lungs, in your blood, and you ionize those important molecules, that could be a problem. That can be very unhealthy. So ionizing power is the ability to form an ion. Okay? The chemical properties of molecules can change, again, like I said, being due to being hit by ionizing radiation. So if you were breathing in dust of ionizing radiation, that dust is emitting particles, and those are hitting your blood molecules. It's probably not a good thing. Okay, and this is going to be fairly dangerous on the inside of the body, where blood vessels are very close to the surface of the tissue. Okay, penetrating power, exactly what it is. This is the ability of radiation to pass through an object. Okay, sometimes radiation can be blocked by objects, sometimes to go through it. Okay, if we look at this little, and this usually should be moving, but in this material it's not. These are different types of radiation we're going to go through in a few minutes. This is gamma rays, alpha particles, and beta particles. So in this case, if you have gamma rays, again, if you have paper which is fairly thin, aluminum is a little thicker, and then lead you're going to have is a thicker piece of dense substance. Okay, gamma rays, again, will go right through the materials. Gamma rays will pass through paper, through aluminum, and be blocked by lead. Alpha particles, on the other hand, are much harder, much larger particles. And again, a gamma ray is actually energy. So this is very, very, very high energy waves, the highest energy waves you can get, really. So very, very far past the violet on the ultraviolet scale. So you can see these have a lot of energy to go through, very, very high wavelengths. Sorry, short wavelength, high frequency. All right, alpha particles are actually particles, okay, and as they go through, they're actually blocked by a piece of paper. Okay, so they're large particles that can be blocked very easily. The skin can easily block them. Okay, beta particles move a little quicker. Those are smaller. They can go through paper, actually, and they are blocked by a small piece of aluminum foil. So this is aluminum foil. they can be blocked by that foil. So you can see this is much more. So this is more ionizing. Okay, this is more penetrating. Okay, so that's the way you can think about this. All right, the larger the mass of the incoming radiation, the lower the penetrating power. So basically, you want to be able to know your penetrating power and your ionizing power based on the radiation that you see here, the gamma rays, the particles, and beta particles. And we're going to look at that in the next slide. All right, so on this slide, we look at the different types. So what actually types of radiations do we have when we look at radiation? Okay, so the first type of radiation is my alpha particle. And my alpha particle is really what my alpha particle is. It's really a helium nucleus, okay, that is a +2 charge. You have no electrons here. So there's no E's attached to an alpha particle. So it is really helium, okay, and where we get our helium from the Earth is really alpha particles that were once radiation that now have picked up a couple of electrons. So alpha particles is little 2 protons. Here's your 2 protons, okay, and your 2 neutrons here. Your little pink guys are your neutrons, your yellow guys are your protons. And again, that makes a little ball here of a nucleus, and that becomes the symbol of helium. Sometimes we have the 2+ that's here. Many times we do drop it because in the world of nuclear, we call them alpha particles, but they really are helium. Okay, your penetrating power in this case is going to be out of 10,000. If we look at our scale down here, 1 being the weakest penetrating power, okay, and 1,000 being the best penetrating power, alpha particles are the weakest. So very, very weak. You can actually use that as, your little tag here. Okay, your ionizing power here is very strong at 10,000. So this is going to be very strong. All right, so you can add that to your box if you need to. Okay, now when do you emit this? When the nucleus is very, very big, we're going to emit alpha particles. When you have a huge nucleus and nuclei are overloaded with protons and neutrons, this nucleus will lose a chunk of itself and you will lose alpha particles. Okay, we're going to hold off on how it's formed for the next slide. We'll get to that a little bit later. Okay, a beta particle is simply an electron. Okay, an electron in chemistry is a negatively charged small particle. However, in nuclear chemistry, we call electrons beta particles, and these can be actually ejected out of the nucleus. Repeat that. Electrons coming out of the nucleus. That sounds a little weird, and it is, but we will get to the reason why this is the case, okay, or why we believe this is the case. Now, it's going to have a -1 charge. Okay, we lose a lowercase e. The mass number up here, again, is going to be 0 because we're going to assume beta particles are so small, we're going to assume they have no mass. Now, of course, they do, but very, very small mass, so we assume 0. And again, the weird-looking atomic number is going to have a -1 here to show that you have a -1 charge. Okay. Now, penetrating power, beta particles are up the middle at 100. Ionizing power up the middle. These are basically high speed. Okay, so these move high speed. Okay, so basically pretty much at the speed of light here, these move quickly. Okay, alpha particles are going to be relatively slow. Okay, that's important to know about them. Also, when are these emitted? When you have too many neutrons. Okay, so if you have a nucleus that has overloaded neutrons, way too many neutrons that's comfortable or stable, you will emit beta particles. Again, a little bit more about this, how they're formed later on. Okay, now a beta particle has a complementary or oppositely charged particle. Sometimes they call these antiparticles. And a weird part about physics and particle physics is the fact that scientists believe that there's an oppositely charged particle to every particle. So if you have a proton, there's antiprotons. If you have electrons, you have anti-electrons. So for when you have electrons, there also is something called a positron. And a positron is simply a positive electron. So instead of saying positive electron, we say positron. A positron is exactly like an electron, same size, same shape. However, it's got a +1 like a proton would be. But it's not a proton because it's very small. So we simply call a positron an anti-electron, okay, or an oppositely charged electron. So again, you have your mass number up here at 0 and a +1 down here as if you would have a proton. You also, again, 100 to the middle, and in this case, you're going to emit positrons when you have too many protons. Okay, so too many protons, again, would be this. And since there's only protons and neutrons in the nucleus, you can only have these 3 conditions. Like, so when would you do this? you can either be too big, which means you have too many protons and too many neutrons or too many protons by comparison. And again, how we're formed, we'll go over this in a minute. All right. You can also emit neutrons. A neutron's traditional neutron has no charge. Again, the weird symbol for a neutron is a lowercase n, but we're going to flip now because you have an atomic mass unit of 1. We're going to have a 1 at the top and a 0 at the bottom because we're going to assume there's no atomic number, which means there's no charge. So again, there's no charge, okay, to these neutrons. Important to know. Okay, neutrons are not going to worry about penetrating power. We're not going to worry about ionizing power because neutrons can be fast neutrons or slow neutrons depending on the speed. Okay, and again, because neutrons have no charge, they were initially difficult to discover because they're not attracted to anything. So how would you find them? Very similar to noble gases. How noble gases were really the last few elements to be discovered because they don't form bonds. All right, so it varies when you emit them. Okay, and lastly, gamma rays actually, in a way, are going to be energy. Don't forget this. This is a very common thing that people make mistakes on, is the fact that gamma rays are not particles. The first few are particles. This is your energy. Again, it's an energy wave, so it has a wavelength. Okay, it has a wavelength and it has a frequency. You know, your F and your lambda. Don't forget those. Okay, it's got no charge. Okay, what we do is we use the Greek letter lambda, and the Greek letter lambda has this little, you can draw it actually as a little infinity symbol that's on its side, like infinity we usually draw like that. So it's actually a Y with a little loop. It's kind of cute. All right, and it's got no mass at the top and no charge, so it would have this double zero kind of thing. All right, the penetrating power of this is huge, very, very big. So it's very strong penetrating power. It goes right through objects. It goes through the human body, causes a lot of damage on the inside and on the outside if you have a lot of gamma rays exposure. Okay, but it's got an ionizing power at 1. It doesn't really do much as far as ionizing. Okay, and again, this accompanies other radiation. So, for example, if you emit positrons, you can also emit gamma rays. If you emit alpha particles, yes, you can also emit these energy rays. And again, where they come from and how they form and how this occurs, we'll get to a little bit later. All right. So just the last thing I want to mention here is looking at the reference table. And again, if you were taking the Regents, you would also have this as part of your you would have this as part of your reference table. So what you want to do with this one is really take a look at, and again, this is table O. Table O actually gives you this information. So you're probably thinking, wow, we just went through everything and I'm going to be given this. But just to know that alpha particle, beta particle, gamma, neutron, positron is on here. Okay, and again, you can, sometimes beta particles could have the Greek letter beta. You'll see here. With the plus and minus, that's also another way that you can say beta particle. And what I didn't mention before was protons. Protons can have a lowercase p with a 1 and 1, okay? Or they can also be hydrogen, because remember, a hydrogen atom is really a proton. All right, so that's there. Okay, and on the other side, on table N, in the first column, we'll give you the radioactive isotope, otherwise known as a nuclide, okay, which is the radioactive version of an element, okay? And the nuclide name. So if you're gold 198, your name would be gold-198. So that is the mass number. Don't forget, it's important. Okay. Half-life we'll get to later on, but the decay mode is an important thing. This is the particle that this element would give off. So for example, if you had a gold 198 nucleus, that nucleus would be radioactive. So again, these are radioactive elements here, these nuclides. Well, if you had a gold 198 atom, that would give off a beta particle. And the beta particle is this particle here. Okay? If you had a plutonium 239 atom, that would give off an alpha particle. An alpha particle is this guy. Okay, so it really doesn't involve you memorizing anything. It's just understanding what the particles are. What this doesn't give you is the penetrating power and the ionizing power. All right, so you want to make sure that you, okay, I'm going to put this here, study, okay, and memorize, okay, the ionizing power, okay, and the penetrating power, because they do not give you this. Okay, but they will ask. All right, so that's an introductory to a little bit of a quick introductory to the particles, the particles you get from radiation. Again, unstable elements will produce this radiation. And we basically have a guide and a prediction process for why and how they do this, but we don't have all the answers. Still under a lot of study. Okay? Take care. We'll see you next time.